Okay. Hello, back again. Time to present the next speaker. Actually, the last regular session speaker for today on this stage. His name is Markus Winnand, and he's a SQL Renaissance ambassador. Introduces the future of SQL into the 21st century. He has a book called SQL Performance Explained. If you're interested, check it out on usetheindexlook.com. There's dashes in between, but you just Google it, use the index look, and you'll find it. It's a free book, right? It's actually free to download, isn't it? Great. And also, if you're interested, if SQL performance is important for your organization and you're kind of lagging on it, and like sometimes we all have problems with SQL performance, you can also hire Markus as a consultant because he does that too. Welcome, Markus. Oops, I didn't want to shoot a pencil at you, sorry.
That was my present, I guess. Hello, everybody. I would like to start with a question, actually two questions. Who of you is using a relational database? Give me a sign. Okay. And then the next question. Who of you is using an SQL database? So you see there's a difference. And that's pretty much the content, the key message of my talk today. Relational and SQL are two different things nowadays. So, you see there on the slides, SQL has a very long history, so I will skip over a few little things, but first of all, I need to get through some legal stuff. Safe harbor statement. No, of course not. Just kidding. But instead of a safe harbor statement, I would like to put you there Save the Planet statement. So I'm traveling a lot, you can imagine. I'm flying here, for example, so my contribution to the climate crisis is more than my fair share. So I try to avoid flying whenever I can, but if I cannot avoid it, then at least I compensate that, I offset that at some climate protection company. And now, something completely different. So SQL, the original paper, was written in '74. And I'm now immediately skipping over to the year 92, because there was this infamous release of the SQL standard, SQL 92. Who has ever heard of that, SQL 92? Only so few. Okay, that's good, actually. I will tell you what was the limiting factor of SQL 92, which was then lifted later on. And SQL 92 was pretty much the last SQL standard release that was limited to the relational idea. So what is that relational idea? Everybody has heard about the relational model, but that's only one part of it. The relational model of that at that time was sort of it was defined in terms of atomic types. They were saying, okay, if you have a table, then everything you can put into this table, in each cell of the table, is basically some value of an atomic type. So you're putting them in there and filling them up. There were a few exceptions, like you could already have the null value, which is not allowed in the purely relational original idea, but was allowed in SQL 92 already. But basically, that was the idea. And then there was a second idea on this model side. It was normalization. Who is afraid of normalization? Of all these levels. Do you remember this 1, 2, 3, 4? How far does it go? Who knows? Who knows? Oh, come on, there's more. There are at least 6. And then there are a few levels which don't have numbers, just names. It's really confusing. But this is not what I want to put emphasis on there. Take the word normalization just in the sense of the natural language word. Forget about all these formal levels of normalization. Just think of making the schema normal for the data to live in. Make it a convenient habitat for the data you want to store. Take it from that perspective and forget about these formal levels of normalization for a while. So the idea there was basically, the data should be stored in such a format persistently on disk, which is natural for the data itself, but is not dependent on where this data is coming from and how this data is coming from, or what you want to do with that data later on. That was one of the key ideas, or key benefits, basically. A consequence of this relational data model is that we need to spread data across multiple tables. And that makes it sometimes a little bit hard to work with these data. Because a single business transaction, a single business case can affect multiple tables. So they were saying, that's a little bit awkward if you need to fiddle around with multiple tables all the time. It would be really, really good if we would have a simple but powerful language that makes it more easy to reformat this persistently stored data model into something more useful for each and every processing purpose. And this is the second side of this relational idea. The relational algebra was used for transforming from the persisted on-disk data model to something that is more useful for your use case at hand. And of course, you have more than just one use case. The same data can be used for several things, like you can show it on the screen, you can have a report, you can have an API that has different needs. There are many different things you might want to do with the same data. And that's pretty much the point of it. The data, as we store it persistently on disk, is hard to change. And that's true no matter what tool you're using. Also, if you're using schema-less databases, let's say MongoDB or whatever, once you have stored, let's say, terabytes of JSON documents, they are hard to change afterwards. Of course, it's easy to add new JSON documents in another schema, but whatever you have already stored is hard to change, no matter which database you're using. And the idea here is, okay, let's make the persistent data model in such a way that it is not depending on what we are going to do with that data or where it is coming from. Make it just a natural home for the data itself so that the data itself feels comfortable there, and whatever we are then doing with that is something independent, and we are using this strong query language to do the on-the-fly transformations. That's a really important idea of SQL, which I've noticed most people didn't realize. And that was SQL 92. Relational data model and transformations, mostly using relational algebra. And then there was the big bang of modern SQL, SQL 99. This was the next standard, and it started with really great news. The relational data model is dead. Yahoo! What a clickbaity title. That was the actual title of a paper published around the time when that standard was released, 20 years ago. Seriously. I'll show you what it means, but first I'll give you 2 quotes out of it. The first goes, to say that these SQL 99 extensions are mere extended interpretations, that's an important term there, an extended interpretation of the relational data model, is like saying that an intercontinental ballistic missile is merely an extended interpretation of a spear. You see, it's somehow, yes, it's related, but on the other hand, it's completely different. And then the second quote. With these SQL 99, with SQL 99, you can get the best of both worlds, and you can get the worst of both worlds. It's upon us, the database practitioners, to do the right thing. And the important message in this quote is, there's the old way to do it, and now there's a new way to do it. And we can freely choose. Both of them are valid. So what is it about? Why is the relational data model dead? What has so dramatically changed on the model side? It starts with a simple question. So I like to quote Chris Tate here because he wrote so many books, it's easy to quote him. So he wrote, I was as confused as anyone else. And if Chris Tate is confused about something on SQL, then this is a really bad sign. So what was he confused about it? It's the atom. What is it? The atom, the term atom, was used to describe what we can put into a single table cell. But people were arguing like, well, of course we can put a string there, but a string is not an atom. You can decompose it into its characters. Same for dates. You can take out the year, the month, the day, and so on. And if you follow this logic, you will end up with the statement, okay, the only real atom of information is the bit. But clearly it was not meant that we can only have a single bit in each cell. So that was the misery they had. So what is meant by that? Everybody had a common agreement and understanding what was meant, but they were searching for a strong definition which actually says what they are meaning. And then Chris Tate wrote on, by the early 1990s, however, it's seen the light. Domains can contain anything, is the quote. And what it means is, well, cells can contain anything. You can put whatever you want into each cell. And that was an interesting finding at that time because we already had these normalization levels, or this first normal form, second normal form, and so on. Like a Jenga tower, out there is a Jenga game you can play. And this definition is actually on the lowest level, on the first normal form, and this was just changed. And instead of finding another word instead of atomic types, it turned out that we can just drop the atomic. And nothing happened to the upper layers of the normalization pyramid. They are still valid. So SQL 99 took that idea up and introduced rich data types to SQL. Of course, we can still use the atomic types, but now it's completely valid to have arrays in a column. In the original definition of the relational data model, there was said like no repeating groups. Has anyone ever heard this? No repeating groups? Okay. So there was, let's give it. So there was an explicit statement that you should not have multiple values in a single column. Now we have a feature there, exactly for that, and it's not breaking this extended interpretation of the relational data model. In SQL, we even have nested tables. Not that I would recommend using them, but we have them. And we have composite types, like for money, where you can combine the currency symbol and the numeric value into a single type, then store it in a single column, and then even enjoy type safety of SQL when you do the transformations. By the way, transformations. It's not limited to relational algebra anymore. And here I would like to give you the very first example with some code. A hierarchy, you know these things. You can implement it, for example, with this parent pointer, where each row has the value of its parent, which effectively implements such a pointer there. And if you have such a hierarchy, you can, of course, pick any of these elements if you know its ID, let's say 42. And then you might have questions like how to find all of these. Let's try to solve that in SQL. So it starts simple. If you know the ID, the question mark is the placeholder for the ID value, 42 for example, then you can easily select the one node. And then you can actually, even in SQL 92, you can do the first step. You can do union all, and then search for all the elements whose parent has that ID, the same value, 42. And then you will get additionally the second layer of this hierarchy. But how to continue? And when it comes to SQL 92, this is now pretty much a game over situation. We could, of course, add more union all, but it's getting really, really ugly, and it's a hard-coded limit. That's not what we want. What we actually would like to express is that we would be able to somehow search on the result of my very own query and use that result again to do again a search. Like when I get the IDs of these two, that I again search for all of them that refer to that one on the parent. And it turns out this is what SQL 99 allows, and the syntax is actually pretty short. Here it is. You can just copy and paste it into any SQL database nowadays, and it will probably run, mostly. What does it do? It actually does exactly that. There's an indirect reference to its own output. That's all. And then you run the query, and you get all of the elements beneath that root node in one go, just a nice list. And this functionality was already introduced with SQL 99 into the international standard, so that's 20 years ago. But the question remains, which databases actually support that? That's why I have these charts. Anyone using MySQL in here? Anyone using MySQL 8? Okay. So you see, it took like 18 years maybe to get it done. But nowadays, pretty much every major SQL database supports that feature. There's nothing against using that. Go ahead, it's fine. It's an internationally standardized feature. It works well. It's widely available. Just use it if it makes sense. So this was just one feature out of SQL 99, and I have to skip over because there are many more things I would like to show you. I'm skipping over to the next standard, 2003. There was another SQL standard, and well, XML was a big hype at that time. And the fundamental change which we had in there in 2003 was that the schema-less idea was taken up. SQL 2003 was actually the year when SQL became a document store. That was the first time a single column, an XML column, could have completely different data in each row. So that was the first time we had this document type of thinking. In the meanwhile, we have JSON, of course. Who's using JSON? Even outside of the database, in some API? Okay. I will show you some JSON examples later on. That was the one part on the model side. And on the transformation side, we have got window functions. Who knows window functions? Oh my God, only like 10 maybe? That's bad. So who knows SQL again? I asked that at the beginning. Yeah. Here's bad news. Window functions are really the killer feature of that decade. If you don't know window functions, you actually don't know nowadays SQL. Seriously. You might know SQL 92, okay, or even 99, but the SQL as it is today without window functions is just not the same. Window functions are a game changer. It has been extended over the years, and it is even popular in these more modern SQL implementations, like Google BigQuery, Hive, Impala, Spark SQL, NuoDB, MemDB, MemSQL, CockroachDB, VaultDB, and probably a few more. You see that ends in 2016. So I guess there are a few more. Window functions is really a game changer. And I would like to give you just a brief introduction so you get the idea. And the example I'm having here is like transactions in a bank account, let's say. So I have a query on the one side. It just gives you two columns. And I have the result it might return out of this database right now. And what I would like to implement in SQL is another column which has the balance after each transaction. So when I start with 0 and put in 10, then the balance should be 10. And if I put in another 20, then it makes 30, and so on and so on. So how to do that in SQL? And it was already possible in SQL 92. There were even multiple ways to do it. You could, for example, just put a subquery in here as another column, like comma, and then select over everything before each transaction. Or you could do a self-join, a theta self-join, who knows that? And a group by. That actually textbook solutions to that problem in relational algebra. But they are actually bad nowadays. Listen what I said precisely. Textbook solutions in relational algebra. But SQL is not limited to relational algebra anymore. And the self-join, as essential as it was in SQL 92, it's almost outdated. It's completely ugly nowadays. Really. Nowadays, you can just directly specify what you want to do. And here we have a window function. The important keyword here is over. That introduces basically a window function. The key idea is that the aggregate functions, like sum, min, max, and so on, they couldn't be used without doing a grouping at the same time before that feature. Now we can do aggregates without doing a grouping at the same time, but we need to specify over which rows we would like to do the aggregation. And that's why we have the over clause. So instead of a group by at the end, I'm putting here the over right after the aggregate function I want to use. And inside the parentheses, I can specify over which rows I would like to run this sum function in that case. And it starts quite odd. Order by. So the last time I checked, 1 plus 2 and 2 plus 1, they were pretty much the same. So why should I possibly order there? And the point is actually, we are soon gonna talk to the database and tell the database something like before and after. These are the terms we're gonna use soon. And for these terms to make sense, we need to first establish a common understanding of the order. So the reason why we put order by in there is just so that before and after makes sense. Because right next, then we can say, over order by ID, rows between unbounded preceding. That's the keyword there. And that means from the beginning of the current data set on and current row. So between unbounded preceding and current row. And at every single row the database is looking, it evaluates this overclass basically and says, okay, between the first row and the current row. And when it is processing the first row, it's of course just the first row, and this will be put into the aggregate function, so the sum of 10 gives you 10. And at the next row, that between already spans 2 rows. And both of them will be put into the sum clause so that you get 30. And so on, and so on, and so on. And there's no self-join or anything. It's just a post-processing of the result once over again in a purely declarative way. So can you use window functions nowadays? Who is still using MySQL 5 dot something? Oh, that might be a reason to migrate. One of the countless reasons. So yes, every major database supports this feature by now. I would like to show you another interesting, not so useful, but interesting feature. Median. So the middle value of an ordered set. You order something, and then you take the middle rows. Just to scare you a little bit, I show you the SQL 92 solution. It's again a valid textbook solution. If you go to SQL 92, this is just fine. It does again this self-theta join, just to number the rows, and then it picks the middle one. And if you look carefully, you will see that we are looking at the same data, at the same table, 3 times. There's a literal self-join, and there's once more looking at the same data source. And again, that is the textbook solution if you are limited to the relational algebra. And frankly speaking, this is how I feel about it. Because it's ugly. It's hard to get right. It's slow. That's the reason why me and people hated SQL in the first place. And it's again the self-join. The self-join is one of these things. If you see a self-join, it's a sure sign that this query was made in the relational world of thinking. They have not yet broken out of the relational algebra thingy. Whenever you see a self-join nowadays, kill it. It's probably wrong. There are only very, very few cases where the self-join performs better than the more modern solution. Very few cases. If you see a self-join, you can probably improve it by now. And if you ever happen to write a self-join, wash your hands afterwards. You must feel dirty then. I do then wash and scrub them, and it's like thick oil. It's like hard to get off, really. That's the feeling I have when I do self-joins. So I have coasters there. You can take them from the white table back there. I've put on some there, and also stickers. Really, remember, when you see a self-join, it probably means that this is still stuck in SQL 92. If somebody is telling you, yeah, no problem, we can use a self-join to solve that problem, stop listening. That guy is probably still 20 years behind. Just saying. So nowadays, just to show you the solution, we have, of course, a more interesting function for that. There's percentile disk. I will show it in a minute. 0.5 is the middle value. Within the group, we can order by something. And this is pretty much the same query as you have seen before. It's just a more modern one, also introduced in 2003. There are 2 different variants. So if you need them, you will understand what the difference is. The one is for discrete values, and the other one is for continuous values. which basically means the one is for categories and the other one does a linear interpolation. Like if you have 4 rows and you ask for the middle value, if you use the percentile disk function, it will be the second value. And if you use the percentile cont function, then it will do a linear interpolation between the 2 values it is in between. Can you use that yet? Well, not so widely as the other functions I've shown you, but you see there is movement. These things are taken up by the vendors. And now I'm making a big jump over to the 2016 standard. There were some other standards in between, but I'm jumping to the recent one right now. So 2016 is the current SQL standard, just in case anyone has wondered. And what we have got there is, amongst others, JSON. Here I have one for you. Of course, you could also store JSON in SQL databases before, because JSON documents are just character strings. The big difference is now that SQL has a semantic understanding of what these things are. So SQL now knows that the square brackets mean arrays and the curly braces mean objects and how the quoting works there and all of that. Now you can ask the SQL database like, is that a JSON thing at all, a valid one? And you will get an answer, yes or no. You can also ask, it's an array, or what type is it? Is it an array? And you can ask, if it is an array, how many elements does it have? We have functions for all of that. And, of course, we have the transformation functions. Because remember back, even in SQL 92, normalization and transformation, these go hand in hand. The hard-to-change data on disk can be transformed on the fly into other forms, like JSON. So we now have functions to transform from a more tabular interpretation to a JSON document, and also the other way around, from a JSON document into a table, like I have it here on the screen. And this is actually the example I would like to show, because it's so short. That's the entire query which does that transformation. The crucial point is here we have this JSON table function. And the first argument it needs is a JSON document itself, so I'm using the question mark here as a bind parameter. The second argument is a so-called SQL JSON path expression. And that serves the very same purpose like XPath for XML. Who knows XPath? Oh, a few. Similar in HTML, we have CSS selectors. Who knows CSS selectors? Oh, also a few. So it's a way to pick some elements out of a document. So for JSON, we have another syntax for that. And if we look at this example that I have here, that's the root marker. So from the root, expect an array and take all the elements. That's the asterisk. And you see, in this JSON document, that gives you 2 results. And that also means this JSON table function will return 2 rows, because this is how we define the number of rows we get from this function. We specify a JSON path expression that just gives us all the elements we should transform into rows. And once we have defined the rows, the only thing that is left is define the columns, and you see the syntax there is also quite simple, like give it a name, give it a type, and then again, use one of these path expressions to tell it where it can find the data, how to populate this column. And there are also modifiers like what to do if there is missing. You can make an error, null on error. You can put a default value. There are many more things you can do just with a simple declaration. And that's the entire example, how to transform this JSON document in a more tabular form, how it is. Unfortunately, this example is quite useless because look what I'm doing here. So the question mark, like I'm sending data from the client to the database, and then I'm querying it back into the client. No, please don't. But now look. That makes sense. We can combine insert with select. So what's happening now is we are sending a JSON document from the client to the database, then transforming that JSON document into this internal table thing and loading all of that right away in this target table. No loop on the client side, nothing. Just sending the data over and storing it. I think that is quite useful. If you can use it in your database. We are here now in the SQL 2016 standard, so that's the most recent one. Although it's 4 years old already, it's pretty fresh in the speed of SQL, so to say. But you see, some of them have it already. And for MariaDB, there's, for example, anyone using MariaDB? Okay. There is a bug tracker, which has the version assigned 10.5, so that's next year's release, probably. It's not yet done, but that's the version that is assigned. On the Postgres side, who is using Postgres? There is a patch. It's in the commit fest. There's no version assigned yet, but there's work done. So it's moving. It's actually moving very rapid compared to how SQL evolved before, or how the implementation of SQL evolved in all these different products. But now I have to rush because, I'm running out of time, so I need a time machine. Who would like to have a time machine? Yeah. Just, hey, database, tell me, how did that table look like 10 minutes ago? Wouldn't that be handy? Mm-hmm. That's what we have now. So in SQL 2011, the previous version, we have got temporal tables and also bitemporal tables. So there are two things. The one is the application versioning, which is there to model when some change happened in the real world. For example, if you have customers, who has customers? Nobody? Oh, that's a startup event here. So if you have customers, you might want to track changes to their master data, because a consequence of the normalization is that you separate the customer master data from, let's say, the order data, if you have a web shop or the like. And if you update the customer data, it looks as though the old orders were placed against the new values. That's bad. It's a consequence of normalization. So we need to have some versioning on the customer master data there. And the application versioning is meant to design how the real world evolved. Like, if people marry and change their name, you will probably not immediately notice. It's not like the first thing after marriage is that you write all your business partners, like telcos and facility, everybody basically. It's not like you tell them, listen, today my name changed. You will first go to honeymoon. And weeks later, you do all this mail work. And your business partners learn about your name change maybe weeks later. And then, as a provider, you need to be in the position to tell, okay, 3 weeks ago, that name has changed. And this is what we have the application versioning for. But I would like to focus on the system versioning today, because that's a little bit more simple to explain. The system versioning models how we learned about these changes. If we enter into our database right now that that name has changed 3 weeks ago, then we learned about it right now. And that's also something interesting to know, because in these 3 weeks, there could something have happened, and we might want to know, why did we still use the old name in that period? So then we have both data there, and that's bitemporal tables. And this second form of versioning is called system versioning, because it can be delegated to the system, to the database system. It can be done transparently. You don't need to change your application for that. That's the really interesting thing there. So there's very little new syntax. It starts by declaring a few things in the table. It's a table-by-table decision. You can have system versioning on one table, but not on another one. That's your choice. And you need to have 2 columns there which define the time frame each row in this table is valid. And you delegate the maintenance of these columns to the database using the generated always as clauses. For the one, you say generated always as row start, and for the other one, row end. And then you need a little bit more syntax sugar down there, and magic happens. If you insert, you don't mention these 2 columns, but the database takes care of it, because you say generated always as. So if you do that at 10 o'clock, it will record, okay, now it became valid, and it's kind of open-ended. We don't know how long that row will be valid yet. And if you do an update, magic. 2 rows are physically stored in the database. The old one is still there. The X is still there. It's just tagged. At 11 o'clock, it became invalid, and a new version became valid. And of course, if you do a delete, nothing is deleted. It's just marked. It's logically deleted if you like to. And if you look at this table and then query it, you get an empty result. It's transparent. The data is there, it's just not shown to you until you explicitly ask for it using, for example, the for system time as of clause. So you say, look at this table as though it was that time. And then you get the data that was valid at that time. Fully automatic. That's the key idea there. Who would like to have that? Who has it? Yeah, there's a small gap. I realized that. Yeah, well, in MariaDB we have it. Who's using MariaDB 10.4 or later? Oh, a few. You can use it. Who's using commercial databases? Oh, at least one. You can use it. You're paying for it. Use it. Okay, so this was something from 2011 already, and also there is some movement. So it's not as rapid as for the JSON table function, but there is some movement. I know that some of these vendors are actively thinking about getting that done. Currently, MariaDB is actually working on the application versioning as well, so that you can have bitemporal tables there as well. Concluding. Here I've made a printout of the current SQL standard. Actually only part 2 of it. It has 9 parts. That part has 1,700 pages. No, don't worry. It's just a cover sheet and empty sheets. I didn't waste so much paper, of course. But what do I want to tell you with that? Compared to SQL 92, we have now 4,000 pages, but SQL 92 had about 750 pages. Nowadays, the SQL standard is about 5 times as big as it used to be. Of course, it's not a really strong way to express feature richness. It's as useful as lines of code. Just if you make a program 5 times as big, it's not 5 times as powerful. But still, it gives you an idea. From that idea on, it also means that if you only know SQL 92, you know at most 20% of SQL. A lot has happened since then. And the story doesn't end here. So the next standard is already in the working. It's called 22X at the moment. We don't know when we get it, in 2020 or 2021. And there we will have things, or this is what is worked on, like graph queries. Anyone knowing Cypher from Neo4j, for example, the graph query language? A thing like that, a match clause like that in SQL. That is what is being worked on the SQL standard right now. The story goes on. But the most important thing to remember from my talk today is SQL is not limited to the relational model anymore, at least not in the way you might have learned years ago. It's not limited to the relational algebra anymore. 80% of the current SQL functionality is outside of this relational idea. And one last thing. If you're using SQL only to run CRUD operations, that means create, read, update, delete, mostly by primary key, then you're not actually using SQL. You might use the syntax of it, but not the philosophy of it, not the idea of it. The idea is to be a bridge between the persistent data model on disk, which is inherently hard to change, and the changing requirements we have all of the time. Because it turned out the data we are working with are not changing as rapidly as the things we are doing with that data. So it is a really advantage if you can have the one thing in a rather static thing, a static form on disk, the persistent data model, and then just transform on the fly. Or even if you get the data, like with the JSON table function, just on the fly transform the JSON table, the JSON object, into this on-disk data storage. That's the idea. More than a query language was the title of this talk. I've told you a query language today. A query language is, for example, the JSON parse syntax. That's a query language. XParse, that's a query language. You can take out a thing of something just as it is, a part of an JSON document, a part of an XML document. That's querying. SQL can, of course, also query, but it can also transform. And I think that is actually the killer power of SQL. And that is what I refer to modern SQL or SQL of the 21st century. I'm running a web page for that, modernsql.com. Who knows that? Oh my God. Thanks for having me. So you can follow my blog there. You can learn about these things. It's, of course, completely free. You can follow on Twitter. You can hire me, as I've been introduced already. And I hope I could open your view on SQL a little bit today, that SQL might be something different than you might have believed. So my name is Markus Winnand. I'm the SQL Renaissance Ambassador, and I thank you for your attention.
Thank you very much, Markus.
And take coasters, take stickers, and catch me for questions. So I think we are running out of time now. I'm here also for the party today, but I have to leave tomorrow early morning. Just catch me if you have a question, right now or at the party or today. Thank you again.
Make sure to take advantage of this, not talking only about Markus. Go and meet any of the speakers at the party, talk with them.